Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of graphing for trig functions, specifically graphing any trig function that's not a sine or a cosine. This is meant for a student who's going through trigonometry, a college level trigonometry course, and we'll cover some of the prereqs here as far as what you should know prior to doing these types of graphs. So first thing we're going to talk about is vertical asymptotes. You should recall that as x gets really close to some value a, I'll zoom in on that there. If f of x, the function values, the y values for your curve, if they go off to infinity or negative infinity, then f is said to have a vertical asymptote at x equals a. Now, to be honest, most of the time that you get a vertical asymptote, it occurs because you have division by zero. It's not all the time, though. There are some functions that naturally have a vertical asymptote. For example, the natural logarithm is one of them. But most of the time, a function has a vertical asymptote just because there's a division by zero at that value of x. For example, you might have something like a function like, let me go ahead and write it, 1 over, let's say, x minus 2 quantity squared. Well, you could see that x equals 2 would cause an issue. So at x equals 2, we actually do have a vertical asymptote for this function, and the function looks something like the following. Let me change my ink color here. Looks like this. So you could see that on either side of this asymptote, the function is climbing to infinity. Technically speaking, it doesn't need to be both sides of the asymptote where the function tends to infinity for it to be a vertical asymptote. It only needs to be one side, but both sides is fine too. All right. So that's one thing we need to recall. The next thing we need to recall is that the period of the sine and the cosine functions, they're both 2 pi. That, I know we're talking about graphing the secant and the cosecant here, but because the secant and the cosecant are reciprocals of the cosine and the sine respectively, their period is likely very similar to the period of the sine and the cosine functions. That's why we're mentioning it here. And finally, even in odd identities, the sine and tangent are odd functions, and therefore the reciprocals are also odd functions. So the cosecant will be an odd function. In fact, let me write that down below. So cosecant is an odd function, and then since the cosine is an even function, well, the secant must be an even function as well. That's just going to help us graph, kind of in the long run, some stuff. All right, and sorry about my screen. It's just my Wi-Fi for some reason is really terrible. It always has been. So here it is, the theorem about the period of the secant and cosecant functions. The period of both those functions is going to be 2 pi. And the proof is pretty much the same as the proof for the period of the sine and cosine functions. In fact, it's actually, I shouldn't say the same, it's actually using the fact that secant, or that cosine and sine are even and odd respectively. So for example, the secant of negative theta, I'll write theta here. Well, that is by definition 1 over the cosine, again, of negative theta, but cosine is an even function, so that's 1 over the cosine of theta. But 1 over cosine of theta, well, that's the secant of theta by definition. So secant of negative theta is equal to secant of theta, which implies secant is even. And now you could do the same thing for the cosecant. cosecant of negative theta is equal to 1 over the sine of negative theta by definition. And sine is odd, so that's 1 over a negative sine of theta, which is a negative 1 over the sine of theta. But 1 over sine of theta is cosecant of theta by definition. And so cosecant of negative theta is negative cosecant of theta, hence cosecant is odd. Cosecant is odd. All right. So those are the proofs for both of those. So we have that down. It is important to note that when you're graphing, using the symmetry of these functions is very powerful if you can. Finally, let's discuss what happens to a fraction when the denominator is tending to 0. This is a critical conversation as we tend to calculus. It is very important to have this discussion. So let's suppose that you have a fraction. The numerator can actually be anything we want, but I'm writing it as 1, but it could be any number you want. You can have it as 11 if you want. It doesn't really matter. But we have some unknown down here. Let's just call it an x because x tends to be the unknown of choice for most mathematicians. And so what we're going to do is we're going to allow x to get really close to 0. Now there's something special about approaching 0 here that we have to kind of talk about which side of 0 we're approaching. So this notation right here, x is approaching 0 and the superscript is a plus. That means that x is approaching 0 from the right. Well, what do I mean from the right? It means if you have a number line and you're allowing your unknown, your x values, to get really close to 0, so it could be that x value or that x value or that x value, you're approaching from the positive side of 0 or the right hand side of 0. We will not, with that notation, allow x to approach from the left hand side of 0. So all the values x is going to be are things like 1/100th and 1/1000th, that type of thing. So and then there's a additional notation. Now x approaching 0 with the superscript of a negative means x is approaching 0 from the left hand side. So that is actually this situation right here when you have inputs that are getting super close to 0, but they're not actually becoming 0, but they're getting really close to 0, but they're on the left hand side of 0 on the number line. That's critical for us to have that knowledge before we can actually talk about what division by numbers that are really close to 0 do. Or I should say, does. Now let's go ahead and suppose that x is approaching 0 from the right hand side. What happens to 11 over x? Well, if you take some examples of numbers like that are close to 0 but still positive, so 1/10 is very close to 0, or 1/100th is even closer to 0, or 1/1000th is even closer to 0. Well, if you take a look at each of these cases, 11 over 1/10 is 110. So all of a sudden the number went from 11 to 110. 11 divided by 100, 11 divided by 1/100th is 1100. So we went from 110 to 1100. And 11 divided by 1/1000th is 11,000. You can see that the closer the number is to 0 in that denominator, the larger that fraction actually gets. So this seems to imply the following. As the denominator gets really small, but it's still positive, the fraction itself blows up. It goes off to infinity. And you could check that out. You could just try a different denominator, like 1 over a million. And you will see that that is going to be 11 million. So the smaller that denominator, and all these denominators are actually getting smaller, 1/10 is larger than 1/100th, which is larger than 1/1000th, which is larger than 1/1 millionth. So those denominators are definitely getting smaller, closer and closer to 0, yet the fraction itself is blowing up. Well, we could do the same argument as x approaches 0 from the left. So suppose that x is approaching 0 from the left-hand side. In other words, you're plugging in very small numbers, but they're negative. What happens to 11 over x? Well, again, same thing. We have 11 over some very small but negative number. Negative 1/10 is very small but negative, and that fraction will become negative 110. If you plug in something a little bit smaller into that denominator, like negative 1/100th, you will get negative 1100. And you could see where I'm going to go with this. So I'm just going to skip and say, what if we were to plug in negative 1/1,000,000th into that denominator? Well, then you'd get a negative 11 million is what that fraction would be. So as x gets really close to 0, but it's negative, that fraction tends to negative infinity. So why are we having this conversation when we're really talking about the secant and the cosecant is really where this conversation should be heading? Why are we talking about this? Well, it's because the secant and cosecant are the reciprocals of the sine and the cosine. Well, technically cosine and sine, respectively. So now we're going to build the secant and cosecant graphs. And rather than point plotting, which is how we built the sine and cosine graphs, what I'm going to do is use the sine and cosine graphs to help us graph the secant and cosecant. And I'll do this just in the order that I've listed them. So we're going to take care of the secant first. So the secant, we happen to know, secant, and I'll call it the secant of x, because we're graphing on an xy coordinate system. So the secant of x is just 1 over the cosine of x. Let's first graph the cosine of x, and then we'll bother with figuring out what are the values for the secant. Now there is the graph of the cosine function, and we know that from previous work. Now we need to graph the secant. Now remember what our previous conversation was. As our denominator gets really close to 0. So let's take a look at when the cosine gets really, really close to 0, because that's when we're going to have issues. And notice, by the way, where cosine is 0. Cosine, remember this blue curve here is the cosine function. It gets really close to a height or an output of 0 at pi over 2. In fact, it becomes 0 at pi over 2 and 3 pi over 2. And in fact, due to symmetry, at negative pi over 2 and negative 3 pi over 2, and so on and so forth. Any odd multiple of pi over 2, essentially, it's going to have division by 0, or the cosine will be 0, and so the secant will have division by 0 at those times. So that means that we're likely to have a vertical asymptote for our secant curve at those times. And I went ahead and drew in those vertical asymptotes where our secant would have division by 0. Again, they occur at pi over 2, so I'm going to mark that here, x equals pi over 2, at 3 pi over 2, and any odd multiple of pi over 2. So 5 pi over 2, 7 pi over 2, a negative 1 times a pi over 2, a negative 3 times a pi over 2. All of those will be vertical asymptotes for our secant curve. Now, as our denominator, the cosine, to bridge back to a previous conversation, as our denominator gets really close to 0, like 1 over 0, but it's not really 0, it's like 1 over 1/1,000,000th or something like that, we know that if that denominator tends to 0, but it's positive, we know that this entire fraction here will tend to infinity. So let's see, where does that denominator get really close to 0 but still remain positive? Look at the cosine curve right here. Its outputs are getting really close to 0. Like here, that height is close to 0, it's not exactly 0. And this height is close to 0, but it's not exactly 0. And this height is even closer to 0 Again, not exactly 0. And this height is super close to 0. Still positive, still above 0, but not exactly 0. So all these values are getting closer and closer to 0. So 1 over those values should go to infinity. So let's see how that works. I'm sorry about that. That just kind of rocketed out of my hands there. But as our inputs get closer to pi over 2, our cosine gets closer and closer to 0, so our y values for our secant will start firing up. Now, one thing about the cosine and the secant, if the cosine is 1, then 1 over that is also 1. That is, the cosine and the secant are the same when the outputs are 1. So just with that dot and the fact that it's rising off to infinity there shows me that likely my secant curve does something like this. Now, let's take a look at the other side of the y-axis. The same pattern, because it's an even function, we have proven that secant is even, it's going to look like this on the other side. So that has the same behavior on the other side. So that black curve right there is the beginnings of the secant curve. Now, the fact that I used the cosine as the base graph and then graph the secant, that is going to be how I always graph the secant. I will graph the cosine first and then bother graphing the secant. So when you're asked to graph a secant or a cosecant in your trigonometry course, you're going to have two graphs. Well, basically you'll have one, but you'll have to graph two functions on it. One being the reciprocal function, which is the cosine, and then the secant. You're using the cosine to kind of base your secant graph off of. Now, what happens as our inputs are denominators for the secant, which is the cosine here? So what happens as that denominator tends to 0, but from the negative side, in other words, from below 0. Again, cosine, its values tend to 0 at pi over 2. You can see the cosine values are getting closer and closer to 0 here, but we already graphed that side. So let's look at this side right here. The cosine is really, the y value right there is close to 0, but not exactly. It's probably a 0.25, negative. And here's like a negative 0.2, maybe this is a negative 0.1, that's like a negative 0.05 or something like that. They're getting closer and closer to 0, but they're negative. And we had seen on the previous page that if your denominator gets closer and closer to 0, but it's negative, then your 1 over that denominator is going to tend to negative infinity. So the y values of our secant on the right-hand side of pi over 2 are going to dive down to negative infinity. Again, at pi, the cosine is a negative 1, and it's reciprocal. What is the reciprocal of negative 1? Negative 1. So if the cosine is negative 1, then the secant is also negative 1 at pi, and you get this beautiful connector right there. And it will actually, by the very same arguments, go that way. One thing I should note here is that the secant, we mentioned it in a previous video, but the domain or the range of the secant is going to be negative infinity. In fact, I'll write this here. The range of the secant, in fact, range of secant and cosecant, are negative 1 or negative infinity to negative 1, including negative 1, and then 1 to infinity, including 1. And basically that means that the secant cannot be anything the cosine is, except for the 1 and the negative 1. They meet up at 1 and negative 1, but otherwise they never meet. So kind of a neat way of visualizing this. And by symmetry, we can go ahead and graph over here as well. So you kind of see what's going to happen with this graph. It's going to look like this on forever. The blue graph is just there as a guideline, but the reality is the true secant curve is none of this blueness. It's all just the black curve there. And it's hard for me to erase, but trying my best. There you go. There's your secant curve. It goes on forever in both directions. And you can see the secant does have domain issues all throughout. It's an infinite number of domain issues, always at odd multiples of pi over 2. I'll write that down below. I'll write it right here. So the domain of the secant is all x values that are not equal to pi over 2. You can see pi over 2 is an issue, plus pi k. And what that means is, oh, and I should note here, k is an element of z, which is the integers. And that should be pretty good. If k is 1, then you have pi over 2 plus 1 pi, or 3 pi over 2. If k is -1, it's pi over 2 minus pi, which is a negative pi over 2. Another way to write this, by the way, is x is not equal to 2k plus 1 times pi over 2. Again, that would be equivalent to saying, because 2k is an even number, plus 1 is an odd, so that means odd multiples of pi over 2. There's two different ways you could write that. But that's a list of all of our domain issues for the secant function, and that is our base secant curve. I would never start with the base secant curve. I would always start with the base cosine and then graph the secant based upon that. Let's do the same thing for the cosecant now. The cosecant is, now that we've done the secant, the cosecant will be kind of quick. But the cosecant of x, well, we know that's 1 over the sine of x. So again, let's just graph the sine of x. So there's our sine function, and you could see that sine will become 0 at any integer multiple of pi. So for example, 0 times pi. Well, that's where the sine is 0, is at 0. So everywhere the sine crosses the x-axis, I'm going to draw a vertical asymptote. By the way, that's exactly what we did with the cosine. Wherever it crossed the x-axis, we drew a vertical asymptote because that's where we got division by 0 for our secant. So in this case, the cosecant will have division by 0 whenever the sine crosses the x-axis. So let's go ahead and draw those in. There, all that red ink is our vertical asymptotes, our vertical asymptotes. And just like we did with the secant, we happen to know that whenever the sine is 1, its reciprocal will be 1 as well. That is, whenever the sine is 1, the cosecant will also be 1. Whenever the sine is -1, the cosecant will also be -1. Again, as our sine tends to an output of 0 but still positive, our cosecant will tend to an output of positive infinity. And positive infinity there. And same thing over here. Negative infinity and negative infinity. And it goes on forever like that. The pattern continues and ad infinitum. So it goes on and on and on. That is the base graph again for the cosecant. You will always draw the sine curve first to graph the cosecant. And that is probably my best piece of advice for graphing secants and cosecants. Graph the sine and cosine first. Then, as you'll hear me say, link to the maximums and minimums and create these parabola-like structures. They're not parabolas at all, but they look like U-shaped parabolas to a lot of students. So I just say create these parabola-like curves. A couple other things since I mentioned it for the secant, let's mention the domain of the cosecant. You can see that the x values are not allowed to be any integer multiple of pi. So I could say that the domain of the secant, of the cosecant, is going to be all x values not equal to some integer multiple of pi. Again, k is an element of the integers. So 1, 2, 3, -1, -2, -3, 0, that type of thing. All right. And the range is the same as I mentioned before, the range of both the secant and the cosecant, negative infinity to negative 1, and 1 to infinity, including the negative 1, including the 1. All right, that finishes out kind of deriving the base graphs. In the next video, we'll actually graph a bunch of different, not a bunch, but we'll graph a couple different secants and cosecants. You really don't need a ton of them to see how they're done.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.